Over the past 10 years, research into non-invasive means of affecting neural activity has increased. This is due to the potential treatment of certain neurological disorders and mental health conditions. If the system is successful, the psychiatric medical field would benefit greatly from this, as it would open up new avenues of treatment.
However, when triggering certain responses in the brain, artifacts can be left behind, which lead to inaccurate readings. So the aim of our project is to create a non-invasive system that removes these artifacts in real time. Here you can see the system diagram, which we will dissect bit by bit to show you how each part works. The system diagram details the objectives we've set ourselves for the duration of this project, the first of which is to create a working phantom head.
The first subsystem is concerned with the generation of brain signals for the rest of the system to measure and process. This was achieved by constructing a custom-to-scale phantom head to replace on-person testing, as seen here. Designed in SolidWorks, the head consists of three sets of components: the base component to provide a structural foundation, a set of inner components to house and guide internal wiring, and two molding components to cast the gelatin head shape. With all these pieces printed, the head is constructed by sealing the base and inner electrodes within the mold before pouring in gelatin for casting. The phantom head can be injected with a voltage to simulate brain function. Electrodes can be placed on the surface to provide tax and to measure the resulting voltage known as the EEG signal.
Reading an EEG signal can be difficult, as they have very small range and amplitude of 20 to 200 microvolts and are extremely susceptible to noise. This is why an amplifying and a noise filtering circuit is required to record the EEG signals. The EEG signal is picked up by active electrodes that reduce the electromagnetic interference experienced by the cable. This measurement is then amplified by the AD620, a low-noise instrumentation amplifier. The instrumentation amplifier removes the common mode noise and amplifies the differential signal by 25 to prepare for filtering. The common signal is then fed back into the body using a driven right leg to increase the total common mode rejection ratio of the system. As EEG signals are composed of different frequency components between 0.1 to 60 Hz, a high-pass filter with a cutoff frequency of 0.1 and a gain of 10, a low-pass filter with a cutoff frequency of 60 and a gain of 25 are built using the salient key topology. These filters remove any additional unwanted frequencies. The signal then heads to the ADC for conversion.
The ADC selected was the ADS8326. This SAR ADC was selected due to its high sampling rate, low power consumption, and low noise values. This ADC reflects a number of desirable qualities found in ADCs used for medical applications. The printed circuit boards, designed in Altium Designer, were initially designed as breakout nodes, used to test each component separately. The PCBs were then designed around single, dual, and quad-channel implementations. The PCBs were designed iteratively, improving in each design. Great care was taken to keep things as similar as possible. The PCB connects to the EEG electrodes, the FPGA, and the power supply together. The board allows the signal to be converted to digital information in order to be processed.
The CPU choice for this project is an Opal XE301 FPGA board. The reasons for choosing this board include parallel processing, exceeding the required clock speeds of the system, enough resources for processes to run it, easy of data transfer, and a sufficiently large RAM capacity. The serial peripheral interface is a communication protocol adopted in this project within the EEG hardware subsystem to the FPGA subsystem, and transfer the EEG gate from the ADC output onto the FPGA for artifact removal and feedback control.
The filter we are going to use to clean the brain signals is called SMA, short for superposition of moving averages. Let me break that down. First, we're going to take brain signals from our head. Then, we split each channel into segments. Calculate the moving average of each segment. Then the averages are linked together to form the artifact of the signal. And finally, this artifact is subtracted from the signal that we started with.
And the resulting cleaned signal looks like this.
Based on the cleaned EEG signal, the control algorithm is coded to interpret whether the volunteer has closed their eyes. This was realized by using a digital bandpass filter to isolate the clean signal's alpha frequencies, which range from 7 to 12 Hz. The running average of the resulting signal is then calculated and squared to better facilitate amplitude detection. Finally, the control output is determined by checking if the running average is above a threshold value. This control signal can now potentially be used to turn tax off.
In conclusion, we feel the system developed this year has fulfilled the aims and objectives. A model head has been constructed to simulate a substitute for human brain activity. The resulting EEG signal has been filtered and amplified to then remove the tax artifact. Finally, the clean EEG signal is used to output a control signal to manipulate the tax generator. The overall system provides a successful proof of concept in the medical field for a closed-loop, non-invasive treatment of neural